So if you guys remember 3 cos theta, that's going to be a circle that opens horizontally, if you want to think of it like that, or opens on the polar axis with a diameter of 3 and touches the origin. In case you just need a little refresher, 3 cos theta. And just, and also let's adjust this as well. Let me make that from -5 to 5. I mean, you could choose how you want it. I'll make that from -5 to 5 as well for y. Oh, 5. And I'll go from 0 to 2 pi. That's fine. So I know it looks like an ellipse, but it is a circle. Trust it's a circle, right? So yeah, pretty easy, right? So that's just a little refresher. There you go. The radius is actually 1.5, but we say it's diameter is 3. And remember, this is considered the positive direction, right? That's positive for theta. That's negative for theta. We know this is just unit circle stuff, right? This is called theta equals 0. That's the polar axis. So symmetric about the line theta equals 0, which is the polar axis. And what this means is that the point r comma theta. So like, let's say, for example, let's think here. Let's make a little table. Actually, I like to do it the other way around. I like the theta first. So let's say theta is, I don't know, pi over 4. No, take it back. We'll say pi over 3. What's cosine of pi over 3, guys? Half. So times 3 is 3/2, right? So the point would be somewhere over here, right? Okay. What if I did, if I added pi to that, right? So I'd have 4 pi over 3. Sorry, I'm supposed to write as r theta. My bad. My apologies. Hold on. I'm supposed to put r first. I meant to put 3 comma pi over 3. My apologies. So if I did -3 comma 4 pi over 3, where's that point? Oh, sorry. That's what I meant to do. My apologies. Yeah, what if I did -3/2 4 pi over 3? Where would that be? Did you go, Adi?
Would that be the same?
Same point, exactly. It'd be the same place. So we know that. And also, I mean, you could have a point down here as well. That'd be 3/2 comma negative pi over 3. So that's also a possibility. So what's happening for that part of the curve? Again, here's our curve. It just looks like this, right? So symmetric by the line theta equals 0, which is the polar axis. And it means that the point, that for a point r comma theta in the curve, r comma negative theta or negative r comma pi minus theta is also on the curve. So this point right here, we call this r comma theta. This would be r comma negative theta, but it could also be expressed as negative r comma negative theta plus pi. No, it's just no, well, no, that's because it's cosine. That's why. The reason why is that we know this to be true, right? Cosine of negative theta equals cosine theta. So it's an even function. But it's an even function, right? Because cosine negative theta is the same thing as cosine theta. Right? So yeah, so this totally makes sense, right? Yeah, because cosine theta would equal whatever r is, cosine negative theta would be the same thing. Now for sine theta, I won't do the calculator. I think you guys know it's up here. So you get this, diameter is 4. So it's symmetric about theta equals pi over 2 now. That's where it's symmetric. And now in this case, because it's an odd function, right? So you have r comma theta. So in this case, we would consider this to be negative r comma negative theta, or r minus pi minus theta. And that's because, again, sine of negative theta equals negative sine theta. So negative r comma negative theta, or if you do a reversal, when I say reversal, like if you were to go, so if we rotate theta this way, but if I rotate negative theta that way, but then if you do a reversal, where you do the negative r value, it would jump over to the other side. So those are just some things to think about in terms of symmetry for this stuff. But let's talk about the algebra here. This is what I really care more about. Okay, so how do we algebraically verify symmetry on the polar curve? Okay, here's what we do. This is what I care more about. So if you want to be smart about theta pi equals pi over 2, we're replacing r theta with r comma pi minus theta, or negative r negative theta. And you get back to the same equation, then that's going to be symmetric about theta equals pi over 2. That's going to help with graphing the more complex ones. Now, if you're symmetric about theta equals 0, the polar axis, replace r theta with r negative theta, or negative r pi minus theta. And you get back to the same equation, then you're symmetric about that line. So algebraically confirm these. So what I'm going to do for this one is replace r with r and replace theta with negative theta. Of course, you get back to the same thing, right? So that's symmetric about theta equals 0. Whereas here, replace both r and theta with their negative counterparts. And the negatives drop out, so you get back to the same thing. So now you're symmetric about theta equals pi over 2. And we saw that graphically, right? We saw that this was symmetric about pi over 2. We saw this symmetric about theta equals 0, right? So we see that graphically, algebraically, it's confirmed that if you replace theta with negative theta to be symmetric about theta equals 0, yes, we get back to the same equation. Whereas if you're symmetric about theta equals pi over 2, you want to replace both r and theta. And the reason we want to replace that, if I show you the filled out notes, because I don't think I did the best job explaining it, to be honest with you. So if I show you the filled out notes, let's just simmer on this one more time before we move on. So this is symmetric about theta equals 0. And why? Because if I rotate theta this way, and call it r comma theta, if I rotate negative theta this way, that's still going to be the same r value, right? The r value does not change, right? Because that's how I plot r. If I were, like, let's say I have like 3/2 comma pi over 3, 3/2 comma negative pi over 3, right? R doesn't change, right? Whereas here, if I did what's this time? So let's say I did like 5 or 6. So let's say I did 2 comma pi over 6. It's not pi over 6 and 1/2. So let's say at the point here, which is at 2 comma let me get a marker this. So say it's 2 comma 5 or 6. Remember, sine of 5 or 6 is 1/2 times 4, right? So there's 2. So what's going to happen here if I go 2 comma negative 5 or 6, right? I'm actually down here, but I want to jump over there, I have to make that negative, right? I have to make that negative to jump up 180 degrees that way. That's why this will be true about this. That's why if I want to be symmetric about theta equals pi over 2, I got to change both r and theta. Both will change. And then of course, if you want to think about like the reference angles or the pi minus, if that's 30 degrees, that'd be 150. That would make sense to be symmetric on the other side of the y-axis, or theta equals pi over 2. And then here, Yeah, you did negative theta plus pi. Yeah, you're adding 180 over here, but then you negative r, get that way, right? That's what's happening here. If you add pi to this, that rotates this way, then the negative r get back. So these are equivalent points. You guys see why these are equivalent points? Does that make sense? Because you're rotating 180, but then you got your negative r to bring it back. Here, again, that was r negative theta, so we want to jump over there, get the negative r, but then this would just be pi minus that if you rotated back the other direction. So I think I hopefully made it a little more clear. All right, let's move on to the next page. And our plan is to get to half of these notes today, and then the homework will be the actual worksheet. The actual worksheet I gave you guys on Monday, we're actually going to start doing that, and that'll be homework over the weekend. And I want to try to give you guys a chance to get a head start on it, because you know, the weekend's coming up. You guys want to enjoy the weekend, right? All right, or maybe we'll go see the Cavs if they show up. No. All right, that was really cool. I have to say, that was really neat. All right, so next up, zeros of polar curves. Whenever you want to graph, you always want to find like x-intercepts, right? When you graph rectangular, right? Kind of the same thing here. So what we do is we try to set y equals 0 and solve for x. That's what we're going to try to do here. So let me actually have this filled out, or beside the blank version. Okay, so that'll help. So we need tools to start graphing those complex polar curves. So like the symmetry is one tool, right? I just showed you that tool on the first page. Now we know what to do about symmetry for theta equals 0 and theta equals pi over 2. Another tool is how to find the zeros, right? So what we're going to do is when r equals 0, r equals 0 at the pole, right? So that's what we're trying to find. The zeros of polar relation or function correspond to the points at the pole on the graph, or r equals 0. So to find the zeros of a polar relation or function algebraically, we set r equals 0 and solve for theta. That's what I'm going to do. Set that equals 0 and solve for theta. Set that equals 0, solve for theta. And the interval we're going to look at is specifically from 0 to 2 pi. One revolution. Okay, one revolution. Should be pretty easy. What do you guys think about the first one? You know your unit circle should be okay at this. Yeah, pi over 2, 3 pi over 2. Got it. Right. And the other one should be pretty easy too. And remember, 0 and 2 pi are both included. 0 pi and 2 pi. Yeah, there we go. Yep. Okay, so that's pretty easy, right? So coming back to the graph, you don't have to draw the graph again, but coming back to the graph, that was that graph, right? It's pretty clear that if I were to do 0, comma pi over 2, right? So if I rotate, I mean, yeah, that point's right here, actually, right? And same thing with 0, comma 3 pi over 2. It's at the pole. And then this graph looks like this, right? So if we plot that, 0, comma r0, right? 0, comma 0 is the pole. 0, comma pi is at the pole. Whenever r is 0, you're at the pole. So, but again, we know algebraic that's what's happening. Yeah. Well, no, but it depends on your angle. So like when, let's say theta is like pi over 4. No, the raise r would be something else, right? It would be 2 root 2. Yeah. So then you would just, locate the circle of a raised to 2 root 2 at pi over 4, which would be probably like maybe like right there, let's say. Something like that. So anyway. Okay, now the fun begins. Yes, 100%. Great observation. Yes, that's good. That's what we're going to do. Only go from 0 to 2 pi, because then you repeat yourself after that. Actually, let's do this. Since you brought this up, let's have a little fun with this here. If it'll turn on. Okay, so we have this, right? What if I made this like 20 pi? Whoa, what happened there? Oh my goodness. There we go. Again. Yeah, what if I did 20 pi? Okay, it should show it tracing over and over again. Look at the top right corner. See how it's like still thinking? It's tracing it over and over and over again. That's what it's doing. See, it's still thinking. still thinking, because I also made the step really small, like 0.1. So I might need to turn it off because it's being, okay, now it's done. But see, if I go back and just did what I wanted originally, 2 pi, stop thinking, right? So that's what we'll do. We only go from 0 to 2 pi because it's just retracing itself afterwards. So that's good observation. I'm glad we discussed that. Okay, limicon curves. Limicon curves generally, these are kind of cool looking curves. They look like this. They have like this inner loop. Kind of looks like that. I know I did a terrible job of drawing it. I know, it's kind of crazy. Trust me, I'll do a better job with the ones we're going to do right very shortly. So we know that these are circles, right? That pass through the pole, and the diameter is on either one of these lines, right? We know this now. If you have k cos theta or k sine theta. But what would happen if we add a constant to the equation, right? What happens if we add a constant? So we're going to talk about it in just a sec. So you think of adding and subtracting constant would move the circle to another location as in rectangular coordinates or in parametric equations. But with polar equations, adding or subtracting a constant does something different. We're going to investigate. So our theta min and theta max will go from 0 to 2 pi. That's fine, right? But now what if we got this? 1 plus 2 cos theta, 1 minus 3 cos theta, 2 plus 4 sine, 3 minus. What does that do? All right, let's punch these in. And we're going to do some conjecture. We're going to like see patterns and then apply those patterns to what is happening. So let's do 1 plus 2 cos theta. So let me change the 1 plus 2 cos theta. And again, if you want to follow along your calculator, go for it. Or you could watch me do it. Okay, so see what happened here. It's almost like a circle in some ways, but not really. So it looks like this. Let me do some tick marks here. 1, 2, 3, 4, 5. That's up. That's process you don't have needs here. That's kind of cool. I like it too. Yeah, you want to 0 to 5. Oh. Yeah, actually, no, I'm glad you did that. So let me show what Adi had. This is really cool. So Adi didn't have the full window. That's okay, not a problem. So you only did half of it, right? Because it's plotting the points from 0 to pi. It's not doing the full revolution. Right? So it's only giving you a portion of what's happening. Now we can make a table, but I think it's a waste of time, to be honest, because I want to show you the pattern. Because if you make a table, sure, but it's just, again, it takes too long. But yeah, we want to go from 0 to 2 pi. Okay, here we go. Okay, so now, what is exactly happening here? So it looks like it hits 3, right? Off to the right. So it looks like it hits 3. It definitely touches the pole. And there's an inner loop. The inner loop is touching, I think, at x equals 1. So it's doing something. And actually, just to see it in motion one more time, let's understand the motion here. So let me go to actually pi over 2. Okay, it did that first, right? So I'm going to try to emulate. And it looks like it's stopping at y equals 1, right? Here. Sorry, I'm just going to want to get all my colors straight. Okay. So it looks like it's stopping at y equals 1. Actually, should go a little higher. Okay. So stopping there. Then
Isn't that diameter greater than 2 though?
yes, I'll explain. Just hold on to that notion. Yes, you are correct. Okay, then it does that loop, right? So it kind of does something like this. It loops down and curls back up and touches here. And then let's finish off with the 2 pi. There you go. have done a little better, but it's okay. It's fine. Let's do another one. Let's do 1 minus 3 cos theta. Change that to a minus. Change that to a 3. Okay, that one's a little more pronounced. It's a little bigger. So now what's happening? Let me do more tick marks. 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4. So it looks as though, let me actually do half of it. So let's go 0.5 pi. Just so you see what's happening. Okay, so it looks like it kind of starts at -2 and goes towards the pole, right? And then it's going to loop around, right? I think that's what's going to happen next. Let's try it again. Let's go to pi. Okay, so it does that. So it comes back and touches y equals 1. Yeah, there's a little bit of dexterity. And touches that -4. Kind of like tying your shoe, I guess. I don't know. That makes sense. And then 2 pi. Yeah, and then it comes back and finishes off the loop. Touches at -1, goes to the pole, and does that. Okay, again, I didn't do great. I'm not an artist, I'm a math teacher. But now, do you guys, so generally speaking, before I get to the next page, hopefully you guys can come up with some of a conjecture here. So R, not Y, R equals, we'll say A plus B cosine theta. You guys see how A and B are somewhat related here? Do you guys see, like, A here's 1 and B here's 2. What's 1 plus 2? 3. 3. What's B minus A? 1. 2 minus 1. 1. Interesting, right? Okay. Okay. Here we see a 1 and a -3. What if I take the absolute value of that and add it to this? Like 4. Well, -4. What's the difference in these values? 2. Okay, so yes, there's a negative. The negative is probably why it goes to the left. But if I were to take the absolute value of these constants and add or subtract it, let's say this helps take the length of the loop. Something to think about. Okay. Don't worry, we're gonna come up with a formula in just a little bit. All right. Okay, let's do some more. Actually, let's do this. Why don't you guys try the next two? I'm gonna do it also. Yeah, so why don't you guys in your table groups, and then I'm gonna we'll come up with a conjecture in just a little bit.
Mr. Reed?
Yes, sir.
Might not be included.
There's a gap.
Yeah, like.
Oh, I'll take a look.
You're that I just my window.
Yeah, but 6.3 number. One, 2, 3.
That looks like a heart, the second one. All right. So you look at the four graphs of how sine versus cosine affect orientation. So I'm going to put a little generalizations here for you guys. Yeah, it's kind of an aspect ratio thing, I'd say. Yeah, go ahead.
Like the export, how do you know where like there's sex? I can figure out where.
It's going to intersect whatever A is. Because if you think about it,
What data is 0, R is 3. That's what's for plus 3. So if there's pi, that's 0. So that's 3.
So just the integer that's subtracted.
Yeah, exactly. It's like here, if I do 5, right?
Yeah.
That's 0. So you get 2. Or if I do negative, sorry, 5 be over here. Yeah, sine pi. Hold on a second. If I do 0, I know that's definitely 2. And if I do pi, yeah, because now you're over here, right? So it makes it 2, right? Okay. Yeah.
Okay, so here are the generalizations.
In real sine for cosine, the horizontal. You see this now. If you see a plus sign in between the constant and the trig function, then you're going to the right or you're going up, right? If you're seeing a negative sign between the constant and the trig function, they're going down or to the left.
So those are the generalizations we're seeing. But the lengths, we've noticed now, like A plus B
is 6 for the first one. That's up to 6, right? A plus B here is 7. Plus 1 down, so it's negative 7. Now, yes, negative B here is negative 4, but B is an absolute value. You think of a constant as an absolute value. So what's going to happen is that the absolute A plus absolute B will be where it reaches. But if it's going down, of course, make it negative. The absolute B minus A, or what think of that, a little tricky. The absolute value of A minus B, or the absolute B minus A, depending on which one's bigger, will select the length of the inner loop. Right? The inner loop here is 2. 4 minus 2 is 2. 4 minus 3 is 1. So I'll give the length of the inner loop.
And we're gonna have a formula for this in just a little bit. Okay. Questions so far? All right, so now let's take a closer look at one of the graphs. 2 plus 4 sine theta. All right, let's examine this a little more. Okay. So the first part, it takes a range from 0 to 2 pi to draw a complete graph once. We see this now. But change the range to 0 to pi just to kind of see the process, right? What do you notice, right? So if we go from 0 to pi, let's go back to 2 plus 4 sine theta. Turn the sucker on. 2 plus 4 then theta. Okie dokie. Graph it. Oh, sorry, I meant to do that. Let me actually expand this to -8 and 8, I'll say. And again, the reason why it might look a little weird just depends on how you define your window for X or Y, so don't worry about it. And let's change this to a pi. Okie dokie. Yeah, so only do the top half, okay? Only the top half. So what we can say here, what do you notice? The curve is above the line A equals 0, right? Just above. Yes, for the range from 0 to pi, exactly. Is that what you're asking, Captain? Yeah, okay, good. Now, as we determine the zeros of this, well, yeah, that's not hard. I know you guys can do that. So replace R with 0. -2 equals 4 sine theta. Sine theta is -1/2. So think about your unit circle. Where is sine going to be -1/2? That's the y coordinate. That's going to be in the third and fourth quadrants, which would be, well, go ahead, Oliver, what we have? And 11/6, yeah. Totally, right. Right, good, excellent. Okay, so what if you're to plot that on a polar curve, right? So I got to pull a graph here, right? So 7/6 is right over here, right? But it's r is 0, so obviously it's coming back to that. But if you think about it, when you plug in, hold on, r equals 2 plus 4 times sine of 7/6. Yeah, you have 2 plus 4 times -1/2. But if I do plug in 0, I do get 2, so I know that for sure. And that for sure. But what's happening is that when it's plotting it, and if I plug in pi over 2, guys, what do I get when I plug in pi over 2? 2 plus 4 times 1. Yeah, so that's why it hits 6, right? That's why it kind of does this. Where is that? That's a 6. But it's going to eventually loop, because I haven't gone to past pi yet, right? Once I go past pi, what's going to happen? It's going to eventually hit this, right? So let's make a small adjustment here. Let's go back to the calculator. Let's change that to 7/6. We'll see it hit the pole after that. Yeah, see, it's hard to tell,
But it does dip below the x-axis. It's that right there.
and then let's have it go to 11/6. So it does the loop.
And it comes back to the pole, but it doesn't finish it off, right? It doesn't quite do that little part from the pole that x equals 2, right?
Doesn't quite do that yet, but it does our loop. And if you think about, what if I plug in 3/2, right?
Pi or 7/6.
Yeah, if I do 2 plus 4 times sine of 3/2, what's 3/2? -1. 2 minus 4 is -2. So you're at -2, 3/2. But here's the thing, on the polar curve, right? When you're at
-2, 3/5. So 3/2 is over here, plus a -2. So what's that really saying, right? Back here, yeah, right, totally.
yes, yes, -2, 3/2 is the same as 2, pi/2. Now you guys get good. And it comes back this way, and then you gotta finish it off, and it just does that. Like that. There we go. Okay, did a little better this time, but anyway. So I know I kind of went off the rails a little bit because I have to fill out the other parts of the notes. And what I just did right now was the other part of the notes, but I'll fill it out anyway. But for the second question, algebra determine the zeros, just 7/6, 11/6. But we didn't see that from part 1, because part 1 we went from 0 to pi. But when you expand the window a little more for pi, yeah, you see, or sorry, for theta, you see more. Ari, you had a question?
I don't understand how -2, 3/2 is a range of values.
It will be in the range because it's from 0 to pi.
But like, what's the entire range? Wouldn't it just be like,
The entire range from 0 to 2 pi. I'm just doing parts right now.
I think it's 7/6. Okay.
So hold on, let me just back up a little bit. I know, because I went off the rails a little bit here. So the first part, we just graphed the top half, right? That's all we did. The second part, we solved for the zeros, but we didn't see those because we only went from 0 to pi. But if I change my graph from 0 to 2 pi, of course I see this in its all its glory, right? So 2 pi, right? You see the whole shebang, right? Okay. Now, what's the range of values for the inner loop? So what we could do for this one, kind of, think about this algebraically. when theta equals 7 pi over 6 or 11 pi over 6, of course, r equals 0, right? So that means that is terrible handwriting on my part. My apologies. That means the loop is generated between okay.
So that means that between,
So it starts. But go ahead.
it means between pi and 7 pi over 6 and 11 pi over 6 and 2 pi is when it goes below the 4 axis.
Right. Right. Exactly.
Q
Mhm.
equivalent from y itself. Like, how does that end up negative? But you can turn the negative.
Well, that's just if you just plot points. If you were to plot like a bunch of theta values, you would see that the r values would be. Well, first off, well, hold on a sec. Let me finish this part.
Two.
Right, because it came back up again. Yeah, but that's just if you're plotting your points, right? I mean, because you are gonna have some negative r values, and then they will. But there is a brief moment. Oh, so I see what you're asking. You're asking this part, like when we, like why that's below. Is that what you're asking?
Yeah,
And then we have that. That's because you have that 2. If you were to compute it, because you have a 2 plus, right? Because sometimes that 4 sine theta is going to be greater than 2. Sorry, that 4 sine theta is going to be less than -2. It just depends. There's a brief moment where that 4 sine theta part, if you think numerically what's happening, it's slightly less than -2. That's what's causing it. That's what if you plot points, you would see it. If you plot like a gazillion points, eventually you start seeing that. Yeah. So you have to kind of look at it from a tabular perspective, I guess. Anyway, let me finish this off. That means loop is generated between those two values. You start at 2, 0, then goes counterclockwise, and we hit the pole at theta equals 7 pi over 6. Right? Because again, where did we start? We started at 2, 0. We went counterclockwise. And when that hit the pole, when I was at 7 pi over 6. So that's the motion of what's happening. And once you hit the pole, the inner loop starts getting created. Okay. Let's finish this off on the next page. All right. Find the points on the graph where cross theta equals 0 and pi over 2. So what you're going to do is this. I'm going to have you guys do this in your table groups. So 0 equals 2 plus 4 sine theta. So I want you guys working that out. Also, we're going to have pi over 2. Wait. Shoot. Sorry, I messed up, guys. My bad. I'm going to say r equals. So when theta equals 0, my bad, r equals 2 plus 4 sine of 0. So r is going to equal just 2. So you have 0.2 comma 0. All right. Then r equals 6. Okay. However, we must also consider theta equals pi and theta equals 3 pi over 2. So that's usually a good kind of like rule of thumb. Like consider those 4 theta values to see what's happening and where the curve should be. I'll let you guys figure those out. How much you get for those two. And again, our zeros we're at 7 pi over 6, comma 0. Nope, other way around. I keep reversing. I don't know why I do that. My bad. Okay. So we also want to know where it crosses at theta equals pi. Okay. What do you guys get with theta equals pi? Yeah, 2 comma pi. Good.
Okay.
Yep, negative 2, 3 pi over 2. Good.
Do you count as if you write the window as radius angle?
Actually, we should write. We gotta be consistent. We should write. I don't know why I'm putting. I don't know why I'm doing that, but yeah, we should write r theta. Yeah, r first, theta second. All right, the symmetries. Let's state the symmetries, guys. So let's try about theta equals. So we see from the graph, it's symmetric about theta equals pi over 2, right? So remember that symmetry. You change r to negative r, and you change theta to negative theta, and you wind up getting well, hold on a sec. Oh wait, this is actually being weird. Give me one sec. Yeah, that doesn't quite make sense what I'm just doing right now. So let's back up a little bit. It is clear it's symmetric about theta equals pi over 2. We saw that, right? Because it's like the y-axis cutting in half. So remember, you could do two things. You could do negative r negative theta, or you could do r comma pi minus theta for the symmetry. Remember, we talked about that. The first one actually fails us. I don't know why, because the second one will work. And I'm not 100% sure why the first one fails us.
Because we have that 2 plus rather than.
Exactly, it does. But let's try this. Let's focus on this one because it should be symmetric about that too. We saw that in the first page of the notes, right? So I'll keep r as is. I'll do 2 plus 4 sine pi minus theta. Now you guys are not going to like me, but we have to use the difference formula, that identity, and that's kind of a pain. We have to do sine pi cosine theta minus sine theta cosine pi, and then work it all out. So work it all out. What's sine pi, guys? 0, so it goes away. What's cosine pi? And it actually will check itself out. You will get 2 plus 4 sine theta. No, we're doing pi. No, the symmetry part.
Oh, it's a dot. Okay.
Yeah, this is so to be symmetric about theta equals pi over 2. There are two ways of looking at it, which we saw in the first page of notes. Either negative r negative theta, which when I tried it, it actually was not going to work. I don't know. Well, I mean, of course, I know why it doesn't work because you have the 2 plus, but it's the same thing as this, and that does work. So it's just kind of a weird phenomenon, but it gets you back to the original. So now we know we're symmetric about that. Okay.
Why doesn't that?
I don't know. It's a great question. It's tripping me out too. I think what time do we get out, guys? 55. Yeah, I'm not going to do cardioid. Now, cardioid graphs, as the name kind of implies, kind of looks more like a heart. We're not going to get to that today because I don't want to really traverse down that path and not really do it justice. Because that'll take a little while. So we'll do that. Actually, I'm not here on Monday, by the way, too. So that's going to be a video I'll have you guys watch on Monday. You'll have a sub. So the homework will be this, guys. Here's the homework. You guys will actually start working on this because we have done pages 1 through 4 of the notes, right? So you're gonna sketch a lemicon here, right? On the first page of the notes. Sorry, the homework, and then second one, you kind of just do more stuff on that. This one, I don't think you guys can do yet. So I'm only gonna have you guys do just number one, just pages 1 and 2 of the homework. So easy homework. Just do pages 1 and 2 of the homework. I'll put in Schoology. You're not gonna do the rose curve because we haven't talked about how to do rose curves yet. So we're gonna hold off on that. Yeah.
It works.
What works?
Look, so if you have a commit, just if you plug in negative R and gives 5, you end up with negative R. It's like 2 minus 4 is 5. Plug in this one, I'm just trying to go hard to take out the share. It's 5, 4 side data.
So, yeah, I still don't know why algebraically not working. Yeah,
No, it should be. It should be. But I just don't know why algebraically it's not making sense for us here. That's why I don't get it. Yeah. No, it should, right.
The shift and a reflection is the same as a reflection. When you think about it.
Yeah, right. So be it.
Oh.